In this class, we'll take up the design of built-up columns. We'll see what are built-up columns, what different types of arrangements are there for tying these columns together, and what IS code specifies about the built-up columns, about their configuration, and about the design of the built-up columns. So this is a part in which you come across this built-up column, IS 800 2007, clause 7.6 and 7.7. I'll find it in page 48 to 51. So this particular part deals with this built-up column design as well as the specification related to the arrangement of members in the built-up columns. Now coming to the built-up columns. So if at all if we have a heavy load coming on the column, or in case the length of the column is large, then we don't find any standard rolled sections over there which can help us in supporting that load, or which can help us in resisting the buckling of the column. Even the compound sections, that is when you combine the flange plates and all, in that case also we find the section inadequate for resisting the load, or the length is very large, and even then after combination of flange plates or different sections together, we cannot get the required radius of gyration over there. So one way to increase this radius of gyration is spread the area farther away from the centroidal axis over there. So as we increase the distance of the area from our centroidal axis, the radius of gyration, the moment of inertia will get increased. For the given area, we can increase the moment of inertia or the radius of gyration there. So that increase in radius of gyration will lead to increased resistance to buckling. That is, the slenderness ratio will come down, KL by R. As we increase this R value, it will result in reduced slenderness ratio, so which can help in resisting the buckling of the column over there. So that is the main theory behind this built up column. So we use in these sections either in case of a heavy load coming on the column, or in a case if it is having a large unsupported length over there. So built up columns, what they consist is they have two or more members arranged together here. So that is the section what we come across in built up columns. So these sections are positioned at certain spacing, and so that will increase the radius of gyration, and which will reduce the effective slenderness ratio of the column. So this will lead to increased load carrying capacity, as I said. Now when you use two or more than two members in a built up columns, they need to be connected or tied together, or they have to be held together by some means. So such a system through which we hold these different components of a built up column together is called the lacing or a batten system. We have two systems by which we can tie the members of a built up column together. Either we can go with lacing system, or even we can use the batten system over there. So accordingly we come across two different types of built up columns. We call them as a laced column or a battened column. So this is a picture which shows the laced system in a built up column, or we call it as a laced column. It is a built up column with a lacing arrangement provided in it. So these lacing system or these arrangements will help in holding the members together. First of all, when I say we have built up column comprising of two or more than two members, here we can see those members which have been arranged or positioned here. So in this first case, two channel sections have been used here. So they have been facing uh, toe to toe or face to face. They have been arranged in this form. Okay, so the two flanges are facing each other in this arrangement. In the second arrangement, the flanges are facing away from each other, back to back. this is back to back. So in both cases, channel section have been used. ISMC channel sections have been adopted here. The way in which they have been positioned are different. So here the plan view, you can see the two flanges are facing towards each other, channel section. In this is the arrangement for this column. So the two flanges are facing away from each other and they have been separated by certain distance. So when I increase this distance, that will lead to increased radius of gyration about the one of the axis over here. So this is the what we are doing here, for increasing the radius of gyration or for increasing the resistance to buckling. So this is one of the arrangement what you can see in these two columns. First column, this is what the arrangement will be. Okay, so at the edges, as at this edge, the lacing have been provided. You can see this bars provided here. I'll come to this part later, but first the arrangement of members within a built up column, let us see about that. So this is when you use the channel sections. Another arrangement is using the ISMB sections, maybe ISMB, ISWB, or ISHB, the beam sections. If I use I sections, so they can be placed side by side in this form. Okay, so this is also possible. We can use such two members for our built-up column. Okay, so this is a tree arrangement. Another arrangement what we can have is four sections. We can use angle sections. Here we have used angle sections here. So this column, okay, angles have been connected by using lacing system in this column. So at four corners, four angles have been provided here. So these have been tied together by again the lacing system here. They will be held together by this lacing system so that this entire section, compound section comprising of maybe two or more than two members, it will act as one unit. Okay, so this lacing system will ensure that they will hold the entire column or all the components of this column. I mean all the sections what have been used in that column, this lacing system will help in holding them together. Okay, so these are different sections that can be used, and when how they can be arranged in a built up column. Okay, so maybe a channel section may be used, or you can use the beam I sections or even the angle sections. So we can have such different arrangements over here. Okay, so this is the built up column. Now I cannot just place these sections, separate them, place them together and leave them like that. What happens is they will tend to buckle individually, or they may be movement or separation of these sections. That is, on loading, on applying the load, they will not act as one unit. This entire column will not behave as one unit. What happens is within their length there may be buckling of individual uh, elements or the individual sections over here. In order to avoid such situations and to make this entire section as one unit, okay, we provide this battened or lacing system over here. So in this figure, what we are seeing is here is this lacing system. Okay, so these are called as lacing, just like we have in our shoes, we tie the laces together. It is just like that. So the two members have been held together, they have been connected by means of these members. These may be angle section, they may be a flat sections also. Okay, a simple flat section, the most simplest section what we can have in a lacing system is a flat section. So they will be provided in such manner in an inclined fashion like this. Okay, so you can have a single lacing system, what you see here, this is a single lacing system, these both arrangements, or here it is a double lacing system. Okay, so two uh, lacing bars, they are crossing each other, they have been provided in this form. Okay, so here there is only single lacing system, a single bar runs for the entire length of the column, I mean in one direction like this, there will not be any crossing of the lacing bars. Okay, so this is how that lacing arrangement has been shown over here. This is how it will be, either single lacing or double lacing. Okay, in addition to this, at the ends we also provide the tie plates. Okay, at the ends there will be tie plates in the columns, maybe in the bigger in the top as well as in the bottom, the column will be provided with these tie plates, and in between this there will be lacing bars which will be provided over here. So this is about the lacing system, the arrangement. Okay, Now when I use these two sections, I can go for increasing the radius of gyration by increasing this distance between the two sections. But what is the limit on that? I can increase this about the, say, individual section will have radius of gyration about y-axis less than radius of gyration about z-axis. That is, y-axis is the minor axis over here. So when I place this uh, some members in a built-up section and decide the distance between them, that will help in increasing the radius of gyration about y-axis here of this compound section. As I increase this distance between the two members, that will lead to increased radius of gyration, but I cannot increase it beyond this radius of gyration about z-axis of the individual member. I cannot change rz of the individual member. That will remain constant over there until and unless the area, the section dimensions are changed. It will not change. So maximum is I can go up to increasing the ry up to rz. Okay, so that will help in deciding the spacing between the two columns over two sections over here in built up column. So that is the limitation what we have. Ry can be brought equal to rz. That is the maximum limit what we can have in this two sections. Okay, but whereas in when I go for providing such four angle sections, there's no such restriction. We can increase that radius of gyration over here. As I increase the distance in x and y or z and y direction, that will lead to increase in radius of gyration about both the axes over here. So that is the way in which we can increase the radius of gyration by choosing proper sections, the number of sections, and the distance between them. Okay, but limitation is there when you have such two sections arranged together. Okay, we can make ry equal to maximum equal to rz. That is what the limitation is. Okay, or else in such sections where four sections have been arranged together, we are free to increase the radius of gyration in both the direction, ry as well as rz. So no problem with such limitation will be there in case of this type of section or this type of built up section. Okay, so coming to the next arrangement, that is a tying arrangement over here, is through battens. Okay, in lacing system we had inclined members which helped us to tie the two components of the built up column together. Okay, now in case of batten system, there will be plates, horizontal plates, or angles, or even the channels may be provided here. So they will help in holding the members together in a built up column. Normally in this what we use is flat plates, okay, of certain depth and thickness will be used over here. So this is the end batten in this. Like we had end tie plate in lacing system, here we have the end batten. These are the intermediate batten. Okay, this end batten will be there at the top and the bottom of the column. Intermediate batten will come uh, within the length of the columns. So this is the battened arrangement. You can see in this figure also batten have been positioned over here for the entire length of the column. Here also we can have chance sections or even eye sections arranged side by side, facing towards each other or facing away from each other. In case of chance sections, such arrangements can be provided. Only thing is the system which will help in holding the two sections or the sections of the built up member together will be through battens. Okay, these are the battens what we have here. Okay, end batten and the intermediate batten. Okay, now coming to our design code is 800. So clause 7.6, that is in page 48, we have the specification given for a laced column over here. So this is about laced column, design of a built up column through using lacing arrangement. So what it says here, so you can go through these things over there. The main things what are required in the design I have mentioned over here. Other than this, we also have some other minor specifications given there. So these specifications mainly are required for arrangement of the lacing system and the design of the lacing system. That is what is listed in this particular session over here. So first is it is about the radius of gyration here. So members comprising two main components, laced and tied, should where practicably have uh, radius of gyration about axis perpendicular to plane of lacing not less than the radius of gyration about the axis parallel to the plane of the lacing. Okay, so first is it says the radius of gyration about the two axes should be same. That is what it says. This is with regard to lacing system here. So what it deals is rz and ry should be same. Axis parallel to the plane of lacing is this z axis. Axis perpendicular to the plane of lacing is this y axis. So that first clause it says that the radius of gyration about these two axes should be same over here. That is what it means. The next thing is, as far as practicable, the lacing shall be uniform throughout the length of the column. So it is better to maintain the same inclination of the lacing bar for the entire length of the column, the width of the lacing bar as well as the thickness of the lacing bar. So they should be maintained same. That is what it means by uniform throughout the length of the column. Then single lacing system on opposite faces of the components being laced together shall preferably be in the same direction. That is, it is uh, face AB and face BC. So these are the two faces what you can see here, AB and CD. Okay, so if you observe, they should be in the same direction. That is, when I look from this side, they should overlap each other. The lacing arrangement what is provided here, they should overlap each other. I should not see something like this when I look it from in case of single lacing system. The lacing bar should run in the same direction on both the faces. That is what that particular clause says. Okay, so like they should be shadow of one another. Okay, so they should run in the same direction. They should, when we look from one of the from one side of the column, they should overlap exactly. Okay, so that is what that clause deals with. Now slenderness ratio. So what it has is the effective slenderness ratio of a built up column should be considered as 1.05 times the effective slenderness ratio what we calculate. Okay, because in order to take into account the shear deformation that will be coming in the column, for that purpose this effective slenderness ratio, the calculated effective slenderness ratio has to be increased. It has to be increased by 1.05 times the calculated effective slenderness ratio. So when you go for calculating slenderness ratio for any built up column with lacing system, then you increase that by 5%, that multiply that by 1.05. Okay, if the length of the column is given to us, when we decide the radius of gyration, knowing the end conditions from the k value, we can find effective length and go for calculating. When we go for calculating the effective slenderness ratio kl by r, so this kl by r will be increased by 1.05 times, and that will be considered in the calculation of load carrying capacity of the column. Okay, so this is the effective slenderness ratio what has to be taken in case of built up column. Now width of lacing bar. So width of lacing bar should be at least equal to 3 times the uh, in case of bolted and riveted connection, so it shall be at least 3 times the nominal diameter of the bolts. So that is to accommodate the bolts over there. So minimum width of lacing bar shall be 3 times the nominal diameter of the bolt or the rivet. Okay, so that will help in deciding the width of lacing bar for us. What should be the width of that bar? Now the thickness of lacing system. So when we have single lacing system, its thickness shall be 1/40th times its effective length. Okay, 1/40th of its effective length for single lacing system, and for double lacing system 1/60th of the effective length of the double lacing system. Okay, so we can go for calculating the length of the lacing bar here. So this will be the effective length of the lacing bar, distance from center to center of the lacing bar, distance from center to center of the connection in this lacing bar. Okay, so that will be the effective length of that lacing bar. So while deciding the thickness of the lacing bar, if at all if you have provided the single lacing system, then thickness should be at least equal to 1/40th of the effective length of lacings. In case of double lacing system, it should be at least be equal to 1/60th of the effective length of the double lacing system. So this will tell us what will be the thickness of the lacing bars. Now angle of inclination. Now this angle of inclination what we measure will be with respect to the axis of this column. Okay, that is an axis passing through the center of this column. That will be the axis of the column. So that will be the longitudinal axis over here. which will be parallel to this length of the column. So the inclination shall be between 40 to 70 degrees, not less than 40, not more than 70 degree, with respect to the axis of the built up member. Okay, so that will be the inclination. Okay, we can go for providing inclination between 40 to 70 degree for whether it is a double lacing or single lacing system. Okay, now coming to the spacing, the maximum spacing of lacing bars, whether connected by bolting, riveting, or welding, uh, shall also be such that the maximum slenderness ratio of the components of main member A1 by R1 between the consecutive lacing connection is not greater than 50 or 0.7 times the most unfavorable slenderness ratio. Okay, so what it has is, when we use the lacing system, so when we connect the lacing system, that will result in a unsupported length of individual members over here. This will be the length A1 here, what it's mentioned in that clause. So this A1 divided by the radius of gyration, least radius of gyration of this individual section, that will be Ry. So A1 upon Ry, or that R1, what is told there, that should be less than 50, or that should be less than 0.7 times the most unfavorable slenderness ratio, that is zero point 0.7 times the minimum of Ry or Rz. It should not be more than that. So it should be less than, should not be greater than 50, or zero point 0.7 times the most unfavorable slenderness ratio. Okay, A1 is the unsupported length of the individual member. R1 is the minimum radius of gyration of the individual member being laced together. Okay, so R1, normally what we have is the radius of gyration about the y-axis will be minimum for the individual member. Say we have used channel section Rz and Ry. Out of these two, which is least, that will be considered as this R1. A1 is the distance between the connections of the lacing system, the vertical distance between the connection of the lacing system. Okay, so that will be A1. Now, design of the lacing system. So this lacing system will be designed for a certain shear force and axial force. Okay, so what will be the shear force is this Vt, transverse shear. So that will be 2.5% of the axial force on the member. Okay, that will be taken as transverse shear, and from that transverse shear, whatever is the uh, this axial force resulting in the lacing member, for that the lacing member will be designed. Okay, so this Vt, what we calculate, will be divided into the equally into the number of lacing planes. Okay, so if we have two lacing planes, then divided by 2. Okay, uh, and accordingly that will be calculated for individual lacing bar. Okay, so it will be acting in a horizontal direction, transverse shear. So due to this transverse shear, what is the axial force coming in the lacing bar will be calculated. We can resolve that along the lacing bar, this transverse shear, then calculate that and check it for that force, whether that lacing bar can withstand that axial force. So that has to be checked over here. And the slenderness ratio KL by R of the lacing bar should not exceed 145. Okay, so KL by R, we know the center to center distance between the connections. Okay, so that will be K will be taken as 1.0. Okay, or for single lacing system, so it shall be zero point 0.7 times the length over there. So that KL can be calculated from here, and R will be the radius of gyration of that section which has been used in the lacing system. Okay, so this slenderness ratio for the lacing bars should not exceed 145. Okay, so here the effective length of the lacing bars for determination of the design strength shall be taken as the length between the inner end fasteners of the bars for single lacing, and zero point 0.7 times this length for double lacing system. Okay, if at all if it is single lacing system, we'll be considering the distance between the inner fastener lines over there. Okay, so that will be taken as effective length. In case it is a double lacing system, it will be considered as zero point 0.7 times the distance between the inner lines of the fasteners. Fasteners may be bolts, or it may be rivets, or it may be weld over here. Okay, so this will be the slenderness ratio of the lacing bars. Now, thickness of lacing bars. we have dealt with this already. It has repeated over here. So that is what the lacing system design is all about. Okay, further in addition, this is about the attachment of attachment of lacing system to the main member. So when you are attaching the lacing system to the main member, so you need to design the connection to transmit the force that is equal to the one calculated in the lacing system. Okay, that is we have calculated the transverse force over there. So the bolting or riveting or welding of lacing bars to the main member shall be sufficient to transmit the force calculated in the bars. Okay, so that transmitted force is nothing but the axial force within the lacing bars what we have calculated by considering the transverse shear. So you need to design that bolts or rivets or welds for that purpose, okay, for that force. So end tie plates, okay, so we'll see all these things when we take up the problem in detail. So end tie plates, we have to design the end tie plates at the two ends, top and bottom of the column. Okay. Now similarly, uh, okay, we can have the battened column also here. So in case of battened columns, okay, so in this also the battening system should be informed for the entire length of the column, and components should preferably have the individual members of the same cross section and symmetrically disposed about their major axis. That is about the major axis, it will be symmetric. Okay, so that will be the clause what it says here. And coming to this slenderness ratio in this case, or the number of battens, okay, that is one more thing here. The number of battens shall be such that the member is divided into not less than the three bays within its actual length from center to center of the end. Okay, when I provide this battens in the column, so whatever number of battens we provide, we should take care that it will divide the entire column in not less than three bays. Okay, so that will be the base what we have here. So this is one bay. When you provide backing system, there should be at least such three bays in the column. So that will decide the number of battens to be provided in the column first. Now slenderness ratio what we considered earlier was 1.05 times the actual slenderness ratio, whereas in Batten system it will be 1.1 times the actual slenderness ratio. Okay, to take into that shear deformations. Okay, shear deformation is nothing but it will tend to shift or sway sidewise. To prevent that, okay, in order to prevent that, this slenderness ratio is being increased. We are considering the increased slenderness ratio here. And the design of pardons what we have here is so we need to first calculate the transfer shear Vt, which is 2.5% of the axial force, and this Vt will be converted into the shear coming into the battens, the vertical shear as well as a movement over here. So this entire batten will be designed as a beam subjected to a shear Vb, which is Vt into C upon Ns, and a moment Vt into C upon 2n. Okay, Vt transfer shear, C center to center between the battens, that will decide over there. N number of parallel planes of battens. Here if you look at this, there are two planes, so such how many number of batten planes will come here. There may be two, there may be four, depending on how many number of phases the battens have been provided here. Yes, minimum transverse distance between the centers of the boards. So these are the boards which are provided. So from here to here, this is the distance. Yes. So knowing these uh, over here, we can find out what is this shear and the moment to which the batten plates are subjected. And we'll be checking those batten plates whether they are sufficient enough to withstand these shear and moment over here. So they have to be designed for this particular uh, force over there, shear and moment. Now the next is about the tie plates. Tie plates are members provided at the ends of battens and laced members and shall be designed by the same method as battens. Okay, so like we design the battens in that way, we need to calculate the shear and moment and decide on that basis, check it for that shear and moment over here. So the next is the size of the batten plates. So intermediate battens shall have an effective depth not less than the 3/4 of the distance. Okay, so that is the perpendicular distance between the centroids. Okay, so this is so the depth of the batten plates should not be less than the 3/4, that is 3/4 times the distance between the centroids of the main members. Okay, that is this depth of the batten plates. Okay, the intermediate batten shall have an effective depth not less than the 3/4 of this distance, and the effective depth of end battens. Okay, what we have is for the end battens, it will be 8 battens. Okay, at the ends, no. The thickness of battens or the tie plate shall not be less than the 1/5 of the distance between the innermost connecting lines of the rivets, bolts, or wets. Okay, so in this size, it is mainly giving us the depth of the batten plates. Intermediate batten plates, what should be the depth? It should be 3/4 times the distance between the centroids of the main member, and for the end battens it shall be 1/5 times the distance between the innermost lines of the bolts or the rivets. Okay, so this will be the depth of the batten plate. Now spacing of the battens in batten compression members where individual members are not specifically checked for shear stress and bending moments, the spacing of the battens or the center to center distance of its end fastening shall be such that the slenderness ratio of any component over that distance shall neither be greater than 50 nor greater than 0.7 times the slenderness ratio of the member as a whole. Okay, this is what we did for the lacing system. If you consider the distance between the clear distance between the two batten plates, okay, so that distance, when slenderness ratio is calculated considering that particular distance, it shall not exceed 50 or it shall not be more than the 0.7 times the worst slenderness ratio. Okay, we'll take up the problem actually and see make these things more clear when we go into the calculations over there. Okay, so as of now you can go through these clauses mentioned in page 48 to 52, clause 7.6 and 7.7 of IS 800 2007.